Hello everyone. So in this pre-lecture tutorial we're going to be discussing the pH scale. Now the reason why the pH scale is used is really because of something that we learned in the last pre-lecture tutorial. Just as a reminder, basically we learned about the equilibrium constant for the autoionization of water, the ion product constant for the autoionization of water, which is equal to the hydrogen ion concentration multiplied by the hydroxide ion concentration. We learned that at 25 degrees Celsius that this value, Kw, is equal to 1.0 times 10 to the negative 14th. And for neutral solutions, that means that the hydrogen ion concentration must be equal to the hydroxide ion concentration, and that would be 1.0 times 10 to the negative 7th molar. So notice how very small this concentration is. And so when we're dealing with hydrogen ion concentrations or hydroxide ion concentrations in solutions, particularly at 25 degrees Celsius, basically we're going to get a somewhat small number, either something on the order of 10 to the negative 1th molar to all the way to 10 to the negative 13 or 10 to the negative 14 molar. And so because of that, then we need to be able to mathematically convert these concentrations into numbers that are a little bit simpler to deal with. And so the way to do that is to take the negative log of these concentrations. And this would be, again, log base 10. And so what that does is it allows us to create values that are just larger than 0 all the way up to 14. If, again, we're talking about solutions at 25 degrees Celsius. Just as a footnote, basically anytime we see this letter P preceding a symbol, usually that means to take the negative log of whatever it is that follows. And so the pH is the negative log of the hydrogen ion concentration. And suppose that we're given the pH and we want to calculate the hydrogen ion concentration back again, then basically what we would have to do is undo the log base 10. And so the way that we would do that is to essentially first divide out the negative sign, so that would be negative pH is equal to the log of the hydrogen ion concentration. And then since this is log base 10, then basically I would take 10 and raise it to the negative pH power on the left side, and then performing the same mathematical operation on the right side just gives us the hydrogen ion concentration back again. So if I want to find a pH value, I would take the negative log of the hydrogen ion concentration. If I have the pH value and want to calculate the hydrogen ion concentration from it, then I would take the pH and raise 10 to the negative pH, and that would give me the hydrogen ion concentration back again. Also, incorporating this into what we learned in the last pre-lecture tutorial, what that does is it helps us to redefine our characteristics for neutral, acidic, and basic solutions, but this time based on the pH scale as opposed to straight hydrogen ion or hydroxide ion concentrations. And so, based on the mathematical relationship between pH and the hydrogen ion concentration, neutral solutions should have a pH of 7, because basically that would be taking the negative log of 1.0 times 10 to the negative 7th, and that would give me 7.00. If I have an acidic solution, I should be expecting values that are less than 7. Now I know that seems counterintuitive at first, but keep in mind that if I have a hydrogen ion concentration of 1 times 10 to the negative 7th, then if this concentration were going to get larger, then the exponent would actually end up getting less and less negative. So if I had a concentration of 1 times 10 to the negative 6 molar, that would be larger than 1 times 10 to the negative 7th, or 1 times 10 to the negative 5th, or 1 times 10 to the negative 4th, and so on. And so as I take the negative log of these concentrations, then that would give me pHs of 6 and 5 and 4 respectively. And so as a solution gets more acidic, then its pH value should decrease because of that inverse log relationship. Conversely, if I have a basic solution, then basically the pH should be larger than 7. Because again, if I have a basic solution, that means that the hydroxide ion concentration begins to predominate, and so that causes the hydrogen ion concentration to get smaller and smaller. So as a result, then my pH value would rise once again because of that inverse log relationship. Now, in addition to what we've just discussed, we can make use of this new P function that we learned about just now in a way that makes relating hydrogen ion concentrations and hydroxide ion concentrations and the value of Kw to each other a little bit easier. So basically, we just went over this relationship in the previous slide, but I'm going to go ahead and take the negative log of both sides. So this would be negative log of Kw. And this would be negative log of the hydrogen ion concentration times the negative log of the hydroxide ion concentration. So if you recall, one of the fundamental properties of logarithms is that the product of logarithms is actually the same as the sum of the logarithms. So basically, invoking this property, that would mean I have negative log of H plus plus negative log of OH minus. And again, if you recall, anytime we take the negative log of something, we call that P. So this means this is P Kw is equal to pH plus POH. And recall that at 25 degrees Celsius, Kw is equal to 1.0 times 10 to the negative 14th. If I take the pKw, that's the negative log of 1.0 times 10 to the negative 14th. Well, the negative log of 1.0 times 10 to the negative 14th is 14. So at 25 degrees Celsius, pKw is equal to 14. So that means that if I have either the pH or the POH, then I should be able to find the missing value using this equation. So if I'm given a pH, and if I want to find the POH, then I would take the pH and subtract it from 14. Similarly, if I have the POH but I don't have the pH, well, I can easily find the pH by taking the POH and subtracting it from 14. So as we're going to see in the example calculations that I'm going to show you in the next slide, that actually comes in handy. So let's go ahead and work a few example calculations. All right. Suppose that I have the following pH, and I want to find the hydrogen ion concentration, and I want to find the hydroxide ion concentration. Now, I think what you're going to find, and as we cover more of these examples in class, there's actually more than one way to get these problems solved utilizing negative logs and using scientific notation. So we're going to go and we're going to discuss these different approaches. I find that some people prefer certain methods over others, and in the end, as long as what you're doing is mathematically sound, everyone should arrive at the same answer regardless. So I have a pH of 2.5. Now, I should be able to find the hydrogen ion concentration by raising 10 to the negative pH, as we talked about on the first slide. If I do that, I get 3.2 times 10 to the negative third molar. Now, I could use Kw. Remember, Kw is H plus times OH minus. So since I already have Kw, assuming we're at 25 degrees Celsius here, and I just calculated the hydrogen ion concentration, then if I take Kw and divide by the hydrogen ion concentration, I should get the hydroxide ion concentration. So again, basically I could do this. Okay, but another approach that I could use is finding the pOH. So as we just learned on the previous slide, again assuming we're at 25 degrees Celsius, 14 minus the pH is equal to the pOH. And so if I go ahead and take that difference, that ends up being 11.5. If I want to find the hydroxide ion concentration, then I can take 10 and raise it to the negative pOH power, or 10 to the negative 11.5. If I do that math, I get 3.2 times 10 to the negative 12th molar. So I'll leave it to you to verify that this actually works out. Whether I use that relationship or use this one, I do end up with the same hydroxide ion concentration. Let's do one more example. So here I have a pH of 11.3. If I want to find the hydrogen ion concentration, then I'm going to take 10 and raise it to the negative pH power. So that would be again 10 to the negative 11.3. If I go ahead and calculate that out, I get 5.0 times 10 to the negative 12th molar from my hydrogen ion concentration. Now, if I want to find the OH concentration, then I could do that by taking 10 and raising it to the negative pOH power. So again, 14 minus the pH is equal to the pOH. If I take that difference, I end up with 2.7. So if I go ahead and plug in, I'm going to take 10 and raise it to the negative 2.7 power. And if I do that, I get 2.0 times 10 to the negative 3rd molar for my hydroxide ion concentration. So we'll be working these types of problems in class in a little bit more detail. We're sort of just trying to develop the fundamental skill set that we're going to need from this point of the chapter on, and so we're going to go and do some more of these problems as reinforcement. Do work on the follow-up assignment. We'll work on the application activity in class tomorrow and then do some additional reinforcement later on. Again, if you have any questions, by all means email or speak to me in class, and I'll see you guys then. Have a good night.